So, welcome everyone to Guided Study Group, week 8 of Math 141. And so today we're going to be going over section 11.3 and 11.4. So basically the two main methods that you're going to use to determine if a series is convergent or divergent. And they are the integral test in 11.3 with p-series test, and 11.4 is the comparison test. It's including the direct and limit comparison. So for 11.3, the concept is really simple, but when you actually come to execute the integral test, you have to make sure that you go through all of those steps before you apply the integral test. And it can take a lot of work, but the concept-wise and the procedures is really consistent. So it's pretty much easy to apply it. So first one is integral test. So integral test saying if you have a function f is continuous, positive and decreasing, continuous, positive and decreasing on an interval from b to infinity, then if you have the series of an with an is equal to f of n with n equal to b to infinity, then it's convergent if and only if the integral from b to infinity of fx is convergent, and it's divergent if that integral is divergent. Now, here, based on this one, a lot of you might make the mistake that this series n equal to b infinity is equal to b for the integral from b to infinity of fx. Now, this is not right. These two only have the relationships based on this theorem over here. But there's nothing in this theorem that will allow you to come up with a conclusion that this series is equal to that integral. Actually, graphically, if you put it out on the graph, it's not going to be equal. So an series, say it's a continuous, positive, and decreasing. So it's going like this. And so the series is basically the sum of these points. But then if you have the integral, you're basically taking the area under this graph. And obviously the fact that you can see that it is not equal, one is going to be the sum of the kind of like the very thin rectangle over here. One is the sum of the entire areas. Of course, the second one is going to, like the integral, is going to be much bigger than the other one. But they only have the relationship based on the integral test. Another part of this section is the p-series test. So we have kind of like a general formula for the p-series. So if you have a series from n equal to 1 to infinity of 1 over n to the p, it is convergent if you have p bigger than 1. And it's going to be divergent if you have p smaller than or equal to 1. Okay, so just give me a second. I'll put your name in the section. So Anthony, can you put, what is your PSU ID? I kind of forgot again. Is it like AAI 5085 or? Sure. Okay. So now we're talking up to P-series. So yeah, P-series, if you have the series from n equal to 1 to infinity of 1 over n to the p, then it's going to be convergent if p is bigger than 1 and divergent if p is smaller than 1. And talking about this, it kind of like reminds us about a harmonic series where you have the series of 1 over n is divergent. So this is going to be the more general rule. This is going to be the module. Now, the concept of this part is like pretty easy, but so we're just gonna come into practice and see things can get really complicated. So, for what value of p does this series converge? Now, this is a very challenging one just to begin with, but I think it is a very helpful one to practice the integral test. So the problem with the integral test, if we come back here, there are three things that we need to satisfy before we can apply it. Is that it have to be a continuous one, positive, and decreasing function. Then you can apply that. But not to mention the fact that if you want to apply it and determine if it's divergent or convergent, you have to do the additional step of finding this integral. So there's actually 4 steps that we need to do here. Now looking at this, with ln of n with n bigger than 3, so n is going to be different from 0. So you have, say, you have fx is equal 1 over x, ln of x to the p. Now we will have ln of x is going to be different from 0 with, here's x is bigger than or equal to 3. ln of x is going to be bigger than 0, and 1 over x is also different from 0. So you have fx is continuous on 3 to infinity. Now it has to be positive. It also is positive, so it's just gonna, it's continuous and positive. Why is it positive? So the two things that comprise this function is x and ln of x to the p. Both of them are positive with x is bigger than or equal to 3. So now we need to find if it's decreasing or not, and to do that, it is related to the materials of Math 140, where you take the first derivative and see if it's decreasing. So you have f prime of x is now one problem of taking derivative here is p. You don't know what value of p is. So in this problem, what I would highly recommend doing is that, and this is also the reason that it's really challenging, that you don't know which p that you should start with. You need p to be a specific number so that you can take the derivative. And so in this case, what I can tell you is that I've tried to take it from p equal to 1 to p equal to -3. And I can give you the answer is that this one is going to be convergent when p is smaller than or equal to -2. So we're going to start from that. But after this section, please try it with p equal to 1 or like p equal to some other values, or p equal to -3 if you wish, so that you kind of like get the idea of how many steps it comprises and how difficult it can get to when you use the integral test. And that's also one of the reasons that most of my friends just avoid using integral tests as much as possible. But there are cases that integral test is the only way that you can solve the problem. So this one, I will start with x equal, n equal, p equal -2. So you have, this one is going to be 1 over x, ln of x squared, take derivative of that. So that this one is going now to equal x squared ln of x to the 4th. Then we have negative the derivative of that, so it's going to be ln of x squared plus x 2 ln of x 1 over x. So this one is equal negative ln of x squared -2 ln of x over x squared ln of x to the 4th. And you can kind of like simplify this a little bit. Negative ln of x -2 x squared ln of x to the 3rd. Now, as we said, with x bigger or equal to 3, x squared or ln of x to the cube are all bigger than 0. ln of x is also bigger than 0. So this entire thing is always smaller than 0 with all x bigger than or equal to 3. Therefore, our conclusion is that we can use the integral test here because it satisfies all of the three conditions that we needed: continuous, positive, and decreasing. Now, when we come to apply it, as I said, we still have the part of finding this integral, 1 over x ln of x squared dx. And this can be achieved simply by, so first, this is an improper integral. So let's go from 3 to t. Now we have, if we put u as ln of x, then you're going to have du is 1 over x dx. So you have, it's going to be du over u squared with the change in variable. So it's going to be x u. 3 is going to be ln of 3. So instead of this, you have ln of 3. Limit t approaching infinity. Negative 1 over u, because that's going to be the integral of that from ln of 3 to infinity. That one is going to equal limit of t approaching infinity, negative 1 over t plus 1 over ln of 3. And of course, here you can see the fact that this thing is approaching 0. So it's going to be equal 1 over ln of 3, which is a number. So it means that it's convergent when p is smaller than or p equal to negative 2. Again, as I said, I know the fact that the answer is going to be p smaller than or equal to negative 2. Therefore, I would highly recommend at home try with p equal to negative 3 and p equal to negative 1. At least these two to see the very big difference between these, that why is it not convergent and why is that convergent for the other value. So that's example 1. Again, for you to use the integral test, always make sure that you satisfy all of the three conditions: continuous, positive, and decreasing before you apply it in. Now, example 2, which series can get the convergence determined by the integral test? Again, you have to have a quick check here to see which one is positive, which one is negative, which one is continuous, which one is decreasing or not, so that you can, especially when the question here is only asking if you can use the integral test to determine their convergence or not. So your job here is just to see if they satisfy the three conditions for integral test. First, for B, we just did that, so this one is usable. Now looking at A, it's a series of sine 2n over n squared. Now, if you look at sine, one problem with sine function, sine 2n over n squared, is that you know the fact that it's always going to fluctuate between negative 1 and 1 as n going to infinity, from 1 to infinity. So it means that when you have sine 2n over n squared, it's going to be one value is positive, one value is negative, so this is the x-axis. And then it's just going to get smaller and smaller, but still it doesn't have the general trend of decreasing. So it's just going up and down. So this one, the answer is no, because it is not a decreasing function. I don't even know if it's positive or negative, and as well, it's also negative for some value of n. So half of the value of n. So not decreasing function and negative. Now B, we already solved it in the previous example. Now let's look at C. C, you have the series from n equal 1 to infinity of 1 minus cosine 2 pi n divided by n squared plus 4n plus 7. Again, the denominator is always positive, so no need to care about that. Now look at the numerator. one problem with the numerator is that, again, the problem with 2 cosine 2 pi n, is that it also fluctuates between -1 and 1. So when you have 1 minus cosine 2 pi n, the value that you're going to end up having is either 2 or 0. Because cosine 2 pi n with n equal 1, 2, 3, or 4, it can be, actually when you look, let's look at the functions again. F is decreasing function. Yeah, 2 or 0. So you're gonna have half of the value. So you're gonna have n, if n is odd, all values equal 0. Because when n is odd, 1 minus cosine say 2 pi or 1 minus cosine 6 pi, it's going to be 0. It's 1 minus 1. So you're gonna have half the value is 0 and half the value is equal to n 2 over n squared plus 4n plus 7. And if you just consider the positive part, because like the 0 one, it doesn't really have any physical meaning or mathematical meaning. So if you just look at this half of the problem, you know the fact that as n increase, the entire fraction f of n will decrease. And so this is a decreasing function. And it's also positive and also continuous. So the answer here is yes, you can use the integral test. So 3 conditions are satisfied. Now the last one, e to the 1 over n squared. So G, the series from infinity, n equal to 1 to infinity, e to the 1 over n squared. Sorry, how this is just keep jumping around. Okay, so for this, now you have to do all the steps again, but you can keep something easy. So if you take fx as e1 over x squared. It is continuous and positive because e to the something is always positive and n squared is also positive on 1 to infinity. So it works. Now we need to check if it's decreasing. So you take f prime of x is going to be x to the 4th e1 over x over -1 over x squared minus e1 over x over multiply 2x. This one is now equal -1 e to the x -2x e1 to the x over x 4th. So this one is just going to equal -1 e1 to the x 1 plus 2x over x 4th. Now with x bigger or equal to 1, now you can see the fact that x 4th is bigger than 0. 1 plus 2x, because x is a positive number, this thing is also positive. e1 to the x is always positive. So you have a conclusion, f prime of x is always bigger than 0 because you have this negative sign here with x bigger than or equal to 1. So it is a decreasing function. So the answer is also yes, you can use the integral test here. So when it's asking you if which series can be determined as convergence by the integral test, then this is what you're going to do. Make sure that it satisfies the 3 conditions of the integral test. So that's all I have for exam section 11.3. Now we're going to 11.4, the comparison test. And I would say this is one of the most commonly used tests when in midterm 2, because most of if you use the integral test in the exam and you have a lot of questions about that will be impractical to put you guys in the exam environment because that would take so much time for you to solve one questions. But if you use but the comparison test, even though it can be challenging to apply sometimes, the procedure is really short, and if you understand the concept and apply them enough and do a lot of practice, then this is really easy. And so this usually is the majority of what you're gonna find in the exam. But that is the previous year. I have no idea how it's gonna look this year. So don't just study this test and not learn about like integral test or the ratio or the root test later. And I would say for the ratio and the root test that you're gonna learn maybe after the break, it's gonna be even more important because it will also link to the materials of the finals. So yeah. And ratio and root tests are easier to use as well. But for this midterm too, it will be majority comparison tests and some integral tests, some p-series, some geometric series, and so on. So keep an eye on that. Don't just study one thing because the integral test can be maybe like one of the most important questions in the exam that if you cannot do the first part, you cannot do the rest as well. So comparison test, we have two parts, direct comparison test and limit comparison test. The direct comparison test allow us to just compare directly if you have two series and with positive terms, this part. Then if an one series is convergence and that the all terms in the sequence, this is terms in the sequence, an is smaller than or equal to bn, then hang on, I think I make a mistake, a typo here. Yeah, this is a bn. So if you have a series, bn is convergence, and you have a series smaller than that with all the series with all terms in the sequence smaller than that, then you're gonna have the smaller sequence also, the smaller series also convergent. And similarly, if you have bn is divergent and you have a series bigger than that, so a smaller one is already divergent, so the bigger one is also divergent. One thing that we all must know in this section is that if you want to choose, say like, so it's all your matter to choose bn. Usually you're going to be given an and asked to determine if it's divergent or convergent. It's your choice to choose what the series of bn is. And so usually and so you have to know if bn is convergent or divergent. There's no point of choosing another series that you have no idea about the convergence of that series. So you have to choose a series that you know if it's going to be divergent or convergent for comparison. And usually people are going to choose p series, like this part, 1 over n to the p, or geometric, some of the commonly series that you already did a lot in the previous section, ar to n minus 1, or rational function. Now the last one, rational function, is usually based on also p series. So say if you have like 2 over n squared plus 4n plus 7, usually the way people is going to compare it with is that maybe they compare it with 2 over n squared, or even if you have n squared plus 7, you can compare it with 2 over n squared as well. 2. Yeah. So it's kind of like the way to choose it, and you're going to see a lot in the practice problems, also in my examples here, and also I think in the suggested problems in the lecture. So just and then we have the limit comparison test. The limit comparison test says that if you suppose that you have again two series with positive terms, if you have limit of n approaching, so you don't compare directly if it's smaller than or equal to or bigger than or equal to, but you're gonna just take the ratio of them. So you have limit of n approaching infinity of the term in the sequence. Remember, term in sequence, an over bn. Do not ever write like limit of n approaching infinity, this, over this. Do not do that, because to do that, you have to know if the series is convergent or divergent or not. So there's no point of just putting the series. You have no idea about the series yet, and that's why you're trying to determine the convergence. So you cannot just put the series in here. So you take the limit of the ratio of the term of a sequence. If it's equal to c, which c is a finite number and bigger than 0, then you have either both of them are convergent or both of them are divergent. And again, usually you're just going to be given the series of an, and it's going to become to your choice to choose what is bn. And in this case, again, you're going to base on this principle up here to choose what is bn. And so it's just going to make your comparison easier. The limit comparison test allow us to, you don't need to have this direct relationship, because sometimes it's hard to do that. You're going to see that in one of my examples here. So limit comparison test can be helpful sometimes, but it's not convenient for you to always take a limit of ratio. Sometimes like the fraction can be really complicated, and you take the fraction, and maybe it's even take more time for you to find what the value of c. So started with the example 3. So is this thing convergent? Now, this is where you use the comparison test. So you have sine square. So the an term is sine square. Sine square n plus 3 over 3 to the n. Now, one thing you can do is that one thing we learn about sine, and I think it applies a lot in the squeeze theorem, is that you always have sine equals from -1 to 1. Now, if you square it, it's going to go from 0 to 1. So here, if we can, so you have 0 is always smaller than or equal to sine square n, smaller than or equal to 1. So if you add 1 in, so it's going to be 3 in actually. 3 sine square n smaller than or equal to 4 plus 3 here. And so this one is always going to be smaller than or equal to 3 over 3n, and bigger than or equal to 4 over 3 to the n. Now, looking at this, we always know the fact that, so if you're just looking at the two functions, bn is 3 over 3n, and cn is 4 over 3n. Now, if you look at these, the first one, you can easily rewrite in the form of a trigonometric series. So it's going to be 3, 1 to the 3 multiply 1 over 3 to the n, and 4 multiply 1 over 3 to the n. So a trigonometric series, and you look at the factor, it's 1/3. It's smaller than 1 by absolute value. So you know the fact that these series to compare with are convergent. So to converge, you have to take this side, as I said, because if you have a bigger series, it's already convergent. The smaller one has to also be convergent. So this is the series that you're going to choose to compare with. So now this is come out. Well, this is just like draft paper. So that kind of like come to there. So we're going to have bn is 4. You don't need bn. You can just write as cn. So you have an is equal to sine square n plus 3 over 3 to the n. It's smaller than cn equal 4 over 3 to the n, with all n bigger or equal to 1. Now, and you have the series from infinity, 1 to infinity, of 4 over 3n is convergent by geometric series with r equal to 1/3. Therefore, by the direct comparison test, you have the series of an is also convergent. So that's how you're gonna do this kind of questions. And I want to emphasize here the part over here. Always write y is the series that you choose to compare with is convergent or divergent by whatever series it is, because it will help you keep track later, especially when you have an exam coming up and they have like 80% of the exam is a ton of series. It takes a lot of time if you don't write down every single thing, because when you look back at it, you're gonna have way too many problems going on at once in your head, and you can easily mess up. And so that's example 3. Now example 4, determine the convergence of these two series. And this is where I said the limit comparison test come into place. You're going to see one fact is that for one of these two series, one can be determined their convergence by the direct comparison test, and one cannot. So that time you have to use the limit comparison test. And so let's start with the first one. So you have infinity n equal to 3. n minus 2 over n cubed plus 1. Now this one, if you compare the term n minus 2 over n plus 1. Now, just looking at both the left side and the right side. Here, if you compare it with like on the right side, it's easier because here you have so if you compare usually, I'm going to compare it with n over n cubed plus 1. Why? Because here easily you have a bigger numerator, so it's going to be a bigger fraction. Now, one more thing, you're going to have it compared to n over n cubed. So it's going to be 1 over n. And this is possible because you have a bigger denominator here and a smaller denominator. And so it ends up with that fraction. And now what you have is 1 over n squared. And one thing I would highly recommend with the rational function, you just choose like the biggest power degree in the numerator and the biggest in the denominator and divide it by one another. Usually that's the case, and you're going to have the series that you choose to compare with. And here, by what we just learned by P series, this is convergent by P series, because P here is equal to 2 bigger than 1 that we just learned. So we have from n equal to 3 of 1 over n squared is convergent by P series. And you have n minus 2 over n cubed plus 1 smaller than or equal 1 over n squared, as I wrote here, with all n bigger than 3. And there's one condition I kind of forgot in the previous example, and this one is that all terms in the series have to be positive. That's why when you look at the value of the n that you started, you can determine if it's positive or negative. And as you can see here, if n is bigger than or equal to 3, numerator is positive, denominator is also positive. So all terms in the series are positive. So by these two, you have the series from n equal to 3 to infinity of n minus 2 over n cubed plus 1 is convergent by the direct comparison test. So now you have the series, and we can use the direct comparison test to determine the convergence. So the second one is going to be hard to use, and this is why. So you have n plus 2 over n cubed minus 1. So if you want to compare it with smaller than or equal to, how are you going to do it here? Problematically, because you have a bigger numerator and smaller denominator. So this thing is actually bigger than or equal to n over n cubed minus 1, right? And it's also bigger than or equal to n over n cubed, which is 1 over n squared. So it's actually bigger than a convergent series. So it doesn't mean anything. If you want to say that it's convergent or divergent, if you look at divergence now, what are you going to compare it with? Right? So you have to, it's going to have like n cubed minus 2 or something, or like n plus n. I mean, that's maybe like n cubed minus n here. And maybe you have like, this is going to equal 2 over n squared minus 1. And so it doesn't really help solve anything. I mean, yeah. So the problem here is that it's 2, so it's going to be 2 over n squared minus 1. So it cannot get you back to things like 2 over n squared or some of the closest series that you can imagine, because this one is bigger than this one, and again this one is convergent, so it's not helpful. So I'm gonna write this thing down so that you guys have something to look at home. n plus, what's wrong with this? So that is that. So the way that we're going to use this is that we're going to use I don't know what's wrong with this thing. Are you serious? Like, just give me a second. I think the pen is out of battery somehow, but I don't have any other battery for it. Oh, this is bad. I've been using it for like a year, so like I didn't actually come to think of there's going to be a point that's going to be out of battery. So let's try it on the other slide. Okay, it's better now. So what I'm gonna do is that I'm gonna continue writing it on the next page because it doesn't seem to work here. Okay, now it works. Bigger than or equal to n plus n over n cubed minus n. So this is 2 over n squared minus 1. And again, as I said, 2 over n squared minus 1 is still bigger than 2 over n squared, so it's not helpful for direct comparison. So use the limit comparison. We have limit of n approaching infinity, an over bn, which is, and you know the fact that you're going to compare it with something similar to like 1 over n squared or 2 over n squared. I'm just going to take 1 over n squared, so that's like easier to use. But if you can use 2 over n squared, it doesn't really matter. It's just going to give you the same answer that is convergent. And you're going to see it here. You're going to have 1 over n squared. So if you find this limit is going to equal n plus 2 multiply n squared over n cubed minus 1. And if you take the highest degree out, what you end up having is that limit of n approaching infinity, 1 plus 2 over n divided by 1 minus 1 over n cubed. And so this is 0, this is 0, so what I end up having is 1. And so by the limit comparison test, you need this is a finite number and it's bigger than 0. So we're going to have, and so because the series that you use to compare with, this one is 1 over n squared is convergent by the p series. So you're going to have this series is also convergent by limit comparison test. Yeah, sorry for the final part of this session is that it just keep jumping around with the slides and stuff. So yeah, so this is what I have. Do you have any questions so far? If not, I'm just gonna end the sections here. I have some practice problem again. I'm gonna post it on, and please feel free to try it out. There are some questions that it looks kind of the same, especially this one, but there was one thing that is different, and I want you guys to notice it. If you have any troubles like working on this at home, please feel free to let me know. I will answer it really quickly. It's like weekend over in Australia, so it's gonna be easy right now to answer. So Thank you for coming here, you guys, and I'll see you guys next week.